Welcome to our webinar series on quality assurance and process optimization for additive manufacturing and the role of computed tomography. With this webinar series, we want to bring insight into various aspects of additive manufacturing or 3D printing. And for that, we have invited specialists from the community who are involved in research or industrial applications. Our webinar series is divided into individual webinars. One of them already took part last month. And these take place at different dates and times, and each session is focusing on a specific industry, technology, and application. The last time, for example, we heard something about aerospace applications from our friends at the Fraunhofer IWS in Dresden. And if you have missed this webinar, it's available for you to watch online. My name is Niels, and I'm spending much of my time here at Ixlon looking at the quality assurance of additively manufactured parts. And I'm your host today. We are very pleased to have participants from roughly 20 countries joining in today. And also some of our competitors are watching today. We are very happy to have you here and hope we can be of help and answer some of your questions that you might have as well. Joking aside, we are all representing one technology and we are happy to have you here. Today in our session, we will have a closer look at an application from the world of ceramics. And I'm very, very pleased to welcome Dr. Giorgia Franci from the University of Padua and Sarah Dina from Kyocera Fineceramics. Giorgia is a research fellow at the university where she's focusing on additive manufacturing of ceramic materials, mainly using direct ink writing. And she works on innovative additive manufacturing technologies and inks for fabricating ceramic and glass components. Sarah is the head of additive manufacturing at Kyocera Fineceramics, where she is responsible for all activities in the field from research projects to the transfer of new processes and materials to production. The two will present the results of a joint research project on direct ink writing of silicon nitride solid parts, and will also in the end give a promising outlook on the next steps for additively manufacturing ceramic parts. And now I will hand over to Sarah. So Sarah, the floor is yours.
Thank you, Neil.
Have fun.
Thank you for the nice introduction. I will quickly introduce a little bit of Kyocera so that you know what we are doing. So the name Kyocera comes from Kyoto ceramics. So all the products that we sell are somehow related to ceramics, even if you see it. So for example, the Kyocera group does produces mobile phones, printers, hip replacements, knives, but also industrial components or automotive components and semiconductor parts. And we here in our site in Selb, we are focusing on producing ceramic parts for industrial applications like for foundry industry or semiconductor industry, but we also do some dental ceramics, but our focus is more on most of the parts that we sell in the field of non-oxide ceramics, like silicon carbide and silicon nitride. And today I want to introduce you a little bit more to silicon nitride and show which great properties this material has and why we did want to do additive manufacturing with it. So that you can imagine a little bit more about the properties of silicon nitride, I compared it to a nickel superalloy, and you can see that the density is less than of silicon nitride is less than half of the density than for nickel superalloys, and mechanical properties like the flexure strength at room temperature are pretty similar, but if you go to higher temperatures, the silicon nitride shows a big advantage because it still keeps high strength. What is also pretty nice is that the thermal expansion is pretty low for silicon nitride, much higher for nickel superalloys. And what is also a nice feature is a high thermal shock resistance, which is not that typical for all ceramics. And these properties make silicon nitride great for applications like nozzles, lightweight structures, such riser tubes like you can see here that are used in foundry industry and impeller wheels, for example. But to keep it a bit more visible, what silicon nitride can do, I will show a quick video. So here you can see a silicon nitride jar that is gluing due to the high temperature that it was seeing in the oven, and we put it in iced water and nothing happens. Of course it cools down, but no breaks or anything. And here you can see a little bit about the great mechanical properties. This steel ball is thrown from a 3.5 meters height on a silicon nitride part. And nothing happens. And even if you go over the silicon nitride part with the forklift, it withstands these forces. And most of you, when thinking about ceramics, probably think about cups or plates, which are quite fragile, but with technical ceramics, you can see that there's a better resistance. Okay. And as silicon nitride also shows a high hardness, it is pretty difficult to machine it and to make complex geometries. That's why doing or producing silicon nitride by additive manufacturing offers a great possibility to manufacture complex geometries that are very expensive to produce with traditional methods, or are even impossible to produce with traditional shaping methods. And this will, of course, also enable to produce complex lightweight structures. So we were very interested in doing additive manufacturing of silicon nitride. And some time ago, we joined the AMITI project. It's an European funded project called Additive Manufacturing Initiative for Transnational Innovation in Europe, where people or groups from academia and from industry are doing projects about additive manufacturing of ceramics. And we started a project together with the University of Padua about additive manufacturing of silicon nitride.
All right, thank you. Sorry, and thank you for the invitation here. Thank you, Niels and Sarah, for introducing the topic. Our group here in Padua works with additive manufacturing since 2013. It is a group which focuses on advanced ceramics and glasses processing, and particularly on porous ceramics. So the group has been active for a very long time with other processing techniques for porous ceramics, such as foaming, and with ceramic polymers. And later, we started working extensively with additive manufacturing as a way to produce high complexity components, which are ceramic based. Additive manufacturing is quite a wide family of processes. You see here the 7 subcategories which are commonly used. There's many ways we can produce an object by additively depositing material. We are using a few of these technologies here in Padova. We're using binder jetting, vat photopolymerization, but today we will focus on the last one category that you see here, which is material extrusion. You might be familiar with material extrusion because that's the most common kind of 3D printer that you see around, the fused deposition modeling that uses plastic filaments that are fused and deposited in a layer by layer fashion. The family is a bit bigger and it involves all processes in which a material is dispensed through a nozzle or an orifice in order to create a shape, create an object. The key for all these processes is to be able to achieve a fast consolidation of the deposited material in order to retain the shape, especially if you work with one material only so that you don't have support systems. The technology that we are using here is direct ink writing. Sometimes it is also referred as robocasting, and it doesn't use a filament. Instead, it uses a ceramic paste, which is deposited at room temperature. And this can be done both by applying pressure, like with compressed air, or also by using a screw extruder. Here in Padova, we're using both. In any case, the consolidation here needs to happen through control of the material and through the employment of an ink with appropriate rheology. So the key here is to have a very specific behavior, which is similar to a toothpaste. So if you, I'm sure you're all familiar with toothpaste. Once you want to take the toothpaste out of the tube, you don't need to squeeze that much. You don't need to apply such a high pressure. It flows very easily upon shear. And this is something we would like in order to be able to work with not excessive pressures and rather economic printers. And at the same time, once the toothpaste is extruded on your toothbrush, you don't want this to flow away. So you want it to keep its shape on top of the toothbrush. And this is exactly what we are looking for when we print. So our material should flow easily, but at the same time, it should keep its shape once it's deposited. Together with Kyocera, we were developing water-based silicon nitride suspension system. So we were employing Kyocera's silicon nitride powders in order to prepare such a water-based ink. Of course, if we are thinking about industrialization and larger scale, to work with water as a solvent is usually a good idea. The last goal would be to produce very complex shapes and components, but in order to do that, we decided to start with dense components. And this is because we want to compare their properties with those of conventionally produced parts. In order to do this, we needed to go through both ink optimization to have this toothpaste behavior, but also through process optimization, in particular, deposition parameters and drying in order to have good quality components. We decided to reach that shape consolidation by using additives. Here you see what happens when we add sodium alginate to our system. Actually, if you mix sodium alginate in water, the two molecules have a weak interaction, so we don't see much happening. The mixture is still very fluid, it flows very easily. But if we mix sodium alginate in a water and organic binder system that we developed, we get what is called non-solvent induced phase separation. So we create a polymer rich and a polymer poor phases, which are partially separated. And this results in a material that behaves much more like a gel. So it flows much less easily under gravity. And this has immediate benefits on the printing process. If we compare two lattice components, two porous structures, which were produced with the same amount of solid loading of silicon nitride powder, the one on the left has only water as a solvent. The one on the right has this water binder system. You see that with only water, we didn't get a good shape retention. We had quite some sagging of the deposited filaments, and also the evaporation rate was uncontrolled and was too fast, and this resulted in extensive cracking during drying. Whereas with the water binder system, we were able to get both good shape retention, no sagging, and also controlled water evaporation rate. So it resulted in non-damaged samples upon drying. With this ink, we produced porous components, lattices mainly, because this is what we usually do. And it's also an effective way to prove that your ink can withstand gravity and can retain the shape. If we take a look at the lattice that we were seeing before, from the side, you see that even unsupported struts can retain their shape, can keep the porosity open in the Z direction. This is usually a sign that your ink is well optimized. And we were also able to print more complex geometries with single walls, thin walls, and good definition. So for porous components, I think we were in a good shape. And then we started to focus on dense bars. Of course, if you want to produce dense bars, additive manufacturing wouldn't be your best option. It's a rather inefficient way to produce such simple shape components. The goal here is to have components that we could test as conventional, as their conventional counterparts. So they will be used for 4-point bending test, for mechanical testing. We printed bars with 60 millimeter length, 7 millimeter width, and 4 millimeters height. You can see the deposition pattern from these pictures here. So you see that it is basically a series of lines, a series of filaments, which are stacked one next to the other and one on top of the other. We were using a nozzle with a 410 microns diameter and a layer height and thickness of 360 microns. This was in order to get some overlapping and some better adhesion between the filaments. Everything was done with the idea of optimizing the density of these bars without having over extrusion and lose quality. But Sarah will go deeper into this optimization later on. So we started printing bars. Here you see a video of the process and how it looks like. So it's really a stacking of filaments of material one on top of the others. As soon as we started printing dense components, we started seeing issues that we weren't experiencing with the porous lattices, mainly warping of the bars and the appearance of big holes at the bottom of the bars. This is something, again, we were experiencing only with dense components. So we believed that it was related with the drying process and issues generated during the drying process. Possible reason for both for warping and for holes at the bottom is the fact that we were printing on a dense substrate. So water could leave the structure only from the top and from the sides of the bar, but not from the bottom. This would result in differentiated shrinkage and in the accumulation of water at the bottom, which would result in the big holes. And we assumed that by printing on a porous substrate, we would solve both issues by allowing water to evaporate in all directions. So we tested printing on 3 different substrates. The first one here is the dense Teflon substrate that we were using at the beginning. And then you see the results on a porous silicon carbide and a porous alumina substrate. The best results were achieved with the porous silicon carbide substrate. Here you still see a couple holes, but these were not caused by the accumulation of water, but rather by the presence of bubbles in the syringe. So these are defects during printing in which the material was not extruded because there was a bubble in place. This is another issue that we will definitely need to solve if we want to optimize this process. But yeah, there were no big pores at the bottom, and then we started to question ourselves whether the same space which was occupied by these holes at the bottom before is now distributed inside the bar.
Yeah, and we were thinking about if we can improve porosity by changing the printing pattern. So the first bars that we printed, those printing pattern that we called aligned printing pattern, because all of the filaments are aligned directly above each other. And if you calculate the theoretical porosity out of this model, you get a porosity of about 8.5%. Nevertheless, we were thinking about a printing pattern where we orient the filaments in a diagonal way, and you get a theoretical porosity of about 6.6%. You can even decrease the theoretical porosity by using a hexagonal printing pattern, where the filaments are shifted so that these holes that you see in the aligned printing pattern get closer as the filaments can settle in between those holes and they get smaller. And what was also interesting for us to see is a bio-inspired structure, the Boolean-Gunn structure, with a theoretical porosity of about 6.6%. And then we analyzed all those different printing patterns in the green state, so after printing and after sintering. So all the ceramics that we produce have the shaping process first, and then they go into the furnace. So we do this sintering step and the parts are finished. What do we do when looking at our bars with X-ray CT, and how does it work? So we place a part, in our case the bars, inside a chamber, and we take 2D X-ray images all over. So we rotate the part 360 degrees, and then we have many 2D projections. And with some algorithms, we can reconstruct those 2D projections and finally get a 3D volume that in the end gives us a 3D solid. We can see in the next slide how this looks like for our printed bar. So we have an aligned printing bar in the green state. And in this short video, we can see how this part looks like looking at it with CT. And we see lots of pores, and the colors indicate the size of the pores. So the blue ones are small ones, and then the red ones are pretty big ones. Yeah, and apart from looking at videos, of course, you can also inspect the single slide and look at some special defects, or just analyze different parts of the bars or your parts. And yeah, honestly, when I first saw the pictures of these green parts, I was kind of shocked. I expected pores, of course. We wanted to see the pores, but I did not expect that it looks horrible. And we have all these cracks and many pores all over the part, like you can see here. And I had a little bit of hope, and I thought, okay, we have this sintering process, maybe it gets better. Yeah, so during sintering, the part, so this is the green part with the microstructure of the green part, and this is the sintered bar, and you see we have quite some shrinkage. And I was hoping that some of the pores will get closed and it will look better after sintering. And you see here the micro CT image of the green bar and the one of the sintered bar below it. And yes, of course, everything gets smaller due to the sintering and the shrinkage, but the number of pores doesn't seem to change at all. Yeah. So we compared the different printing patterns, and I wanted to see if we can see that there is a difference between the amount of porosity between the bars. So looking at the measured porosity for the different printing patterns, it is between 2 and 2.7%, but it does not really relate to this theoretical porosity that we calculated at the beginning. The volume shrinkage is almost the same for most of the parts. One of it was broken. It was not so easy to transport them in green state, especially to the CT, but most of it survived. And for the apparent density, the printing patterns show more or less the similar density for aligned hexagonal and diagonal printing pattern, but the Boolean structure shows a much lower apparent density of only 2.5. And we wanted to check if we can see the reason for this low density in micro-CT. And you can also see a small video of the bar. And you can already see this long crack here. That you still see here in red. And the many, many blue pores. And of course, we looked at it also with some images, and you can see that this crack is really going almost through the whole length of the bar, and also pretty much also to the width. So this explains the lower density for the Boolean structure. This might be related to some printing defect or some defect during sintering. This is difficult to tell with just one bar. And of course, we also compared the different printing structures and the pattern of the porosity, or we checked if there was some pattern of porosity. But as you can see here, there's not real some pattern that relates to the printing structures. All of them show many small pores. They have, of course, like we saw for the Boolean structure, some of them have bigger cracks or some bigger defects, but more or less only small pores, all homogeneously distributed over the bars. And we wanted to see what we can see with SEM, and we cutted one of the bars and looked at the polished surface, and we saw, of course, some pores, but less than in the CT images. But of course, the advantage of the SEM is that you can learn a bit more about the microstructure of the bar. And what we can see here that we didn't see in the CT image is that the pores are related to the printing structure. So this is an aligned printing bar where the filaments were sitting all above each other, and you can see those pores, and these blue circles indicate the filament. We have a distance of about 255 microns. Georgia already told that we have a printing with 360 micrometer layer thickness, but we have some shrinkage during drying and some shrinkage during sintering, and then we get to a distance between these pores of about 255 micrometers. So this pretty good relates to the printing pattern. And another thing that we wanted to investigate is the difference between the printed bars and bars that were produced by isostatical pressing like we do in our conventional production. And what we can see here is that we also have many pores, but the pores are smaller and seem to be a bit more or not homogeneous, but wider distributed. We have what you can do with the micro-CT data that you get is you can look at the sphericity of the pores and also at the pore volume. And this is what we did for this comparison between a hexagonal printing pattern bar and the isostatically pressed bar. And for the isostatically pressed bar, the one with the blue dots, we see that we only have pores with a very, very small pore volume. And the sphericity shows some distribution, but it gets not too low. And looking at the hexagonal printing pattern, we see that we have much more pores with a higher pore volume. And what is even more critical is the low sphericity, because if in ceramics, cracks are pretty dangerous, that you can get some breaks or defects, and therefore we definitely have to reduce those pores, of course, the big pores anyway, but especially sphericity should be higher. Okay. So what did we learn from the CT investigations? So up to now, we did not see any correlation between density and the printing pattern. But of course, we could do some more analysis to get some more statistics to see if this is really the case. And what we definitely learned is that we have a potential for improvement. So we think we can improve the parts by slight changes in ink viscosity and by degassing of the ink that was not done before. And it could take out some of the air and reduce the small pores. And another thing that we want to check is if the mechanical properties are related to the printing pattern. And this is something that is still to be done.
So Sarah was mentioning that there's a lot of potential for improvement. I definitely agree with her. We've seen many bubbles, and this is probably air entrapped within the ink, which is already there at the beginning of the printing process. This is one of the disadvantages when dealing with direct ink writing. We were mentioning we can control consolidation through rheology, through shear thinning behavior, the toothpaste-like behavior, but this also means that we work with high viscosity materials, and once you have entrapped bubbles inside the high viscous materials, it's very hard to get them out effectively. So as possibility to overcome these issues, we are presenting now some of our latest work with the hybridization of additive manufacturing technologies. So I will present you some new possible alternatives to overcome this problem. Direct ink writing, we went deep into the process already. VAT photopolymerization is another very common additive manufacturing process, especially with ceramics. Here we have a UV sensitive, a photosensitive liquid VAT, which is selectively cured using a light source. It has advantages, of course. It's the highest resolution technology available. It also has drawbacks. You need to work with a low viscosity material. This usually means with ceramics that you can have only a small amount of particles suspended in the resin, in the photocurable part, and so a low solid content. It's very hard then to sinter to density. Also, if you need to illuminate your part, you need to allow the light to go through it. So you need some transparency. And you were looking at the inks being printed, they are anything but transparent. So it will be hard to work with silicon nitride powder. Not impossible, but hard. By trying to combine these two technologies, we hope to overcome the limits of both. So we develop an add-on for our direct ink writing system, and which became a hybrid direct ink writing UV system. We added UV LEDs as a light source right after the extrusion tip. And in this way, we could work with much lower viscosity materials, because here the consolidation is given by the UV curing, the fast UV curing of the filament. It doesn't need, the material doesn't need to be that transparent as with VAT photopolymerization, because it's enough if we only cure the outer skin and not the full filament. This has definitely advantages because it's much faster in shape retention, so we can gain complexity. We could print some freestanding supportless components, but it can also have advantages for printing dense bars. Here you see some examples of what we call freestanding components. So this is a spring being printed without any support, and you see that the material consolidates very fast thanks to this UV light addition. There is another big advantage. Sarah was mentioning that many green parts were broken upon transportation. So the green bodies that we were seeing before were very fragile. After drying, they could be damaged also simply by handling them, by moving them from the printer to the furnace for sintering. By using photocurable polymers combined with the silicon nitride powders, we could develop much stronger green bodies, flexible green bodies, as you see here. The spring really is a spring, and it's not damaged by this solicitation. We were not interested only in springs, of course. I think this process could be suited for the production of more complex components. Here you see truss, theoretically stretch-dominated base structures that we are aiming to produce with such technology. If we go back to bars, this could be an advantageous process also for that, due to the fact that the material has a lower viscosity. So our idea here is to selectively switch on and off the UV LEDs, meaning that we could print with UV light on once we print the perimeter and create like a box for the silicon nitride material, and then we leave the UV light off when we deposit the core. So in this way, the core would have a much lower viscosity. It will sag more into the structure. It will fill the pores that are left by the printing pattern, and possibly also release some of the entrapped air, if it's still there. Just to give you an idea of the difference of behavior between the material with and without UV curing, here you see viscosity recovery test. Once the material is at rest before UV curing, it has a certain viscosity. If we shear that, simulating what happens when we extrude the material through the nozzle, we see that the viscosity decreases, and then we release the shear stress, and we see what happens. And if we don't illuminate with UV, we see that the viscosity goes back to the previous value, but it takes quite some time to do that. Whereas if we illuminate with UV light, we see that the materials becomes almost solid within seconds. So the viscosity increases by 3 orders of magnitude in the first couple seconds. So in this way, we can clearly work on the structure, keep the resolution, keep the shape of the bar, and at the same time allow the material to fill this perimeter box. So now I would love to show you that those bars are already better than the previous ones, but we don't know yet. So bars are being fabricated at the moment, and the sintering and the CT scans will definitely follow soon. So this is our conclusion so far. So we were able to produce inks, to optimize inks for direct ink writing, which could work for both porous components and dense components. We reached densities above 97%. We did see that the components were definitely not fully densified. Another good aspect that we didn't mention is that there is a good welding between the filaments. We couldn't detect any interface between the touching filaments, neither in the grain nor in the sintern state. Of course, there was a lot of entrap there. We saw that, which resulted in printing defects and in a lot of residual porosity. And another issue which is common with this sort of additive manufacturing processes is that there's a high variability of both ink behavior and printing parameters. So it's not really an automated process yet. You need an expert operator to select the right pressure, the right flow rate, to take account of the humidity of the environment. So there's still work to be done in order to fully automatize this process. And in terms of what we want to do, the follow-up of this work is testing these bars for 4-point bending test. This was the aim since the beginning. So we want to see if there's an influence of the layers layup, if not on the porosity, maybe on the bending strength and on the fracture behavior. And also, of course, we want to improve the components. So we'll try to decrease these printing defects and voids, either by degassing or by testing this new selective curing, this new hybrid method. This would be it for our seminar. If you want to know more and to go deeper into our collected data, you can and are very welcome to read our full paper, which was published last year in Open Ceramics special issue on additive manufacturing. And with this, I will give back word to Niels, and I will thank you for your attention.
Yeah, thanks, Georgia. Thanks, Sarah, for showing us the results of the research. I think we all learned that not all the time everything works out, and that it's also still a very, very good result to come up with anyways in research and in developing new technologies. And I thank you very much for sharing that with us. Oftentimes in talks and webinars, you only see what works and how great everything is. And that's actually not the reality of research. We also, yeah, thank all of you guys listening, asking questions. Whenever you have more questions, you see all of our contact details here. We will have them shown in the last slide, but now in the meantime, we will switch over to the Q&A session, and we are happy to receive questions from you, and hopefully we'll be able to answer them all. So I will go through the question, read them out in English, and they are all being asked in English. That's good. So I will leave out the names for data protection reasons. So the first question is the lower density due to the effect of porosity formation during printing process? So the lower density probably meaning, yeah, obviously in the printed state. So is the lower density due to the effect of porosity formation during the printing process, or I assume the question is also, or could it also come from gases inside the ink?
Yeah, I think it's more of that. So I don't expect pores to develop during printing. What I expect is to have some air entrapped within the syringe, within the ink, and this will be distributed among the filaments once they are being extruded. So that's for the porosity, which is within the filaments, inside the filaments. And then there is also, as Sarah was showing from the SEM, there is also pores that actually arise from the printing pattern itself. So from the way the filaments are stacked at the interface between them, there can be some residual pores that is not completely filled. So in this sense, it develops during the printing process, but it's not some gas formation during the printing process.
I think that's an important point. We saw that in a totally different study with totally different customers, but we also saw pore formation in printing, like adding additively manufactured structures on metal parts and seeing a lot of porosity in the transition zone. And in the end, we all found out that the porosity is actually coming from the substrate. So obviously in this case, it's the ink, but sometimes the reason is not in the process itself or in the, like in the printing, but sometimes, yeah, in the ink or in the substrate or whatever. So sometimes it's worth to look left and right. So the next question is, what are the current mechanical properties of the bars? I think I can answer that. We have not yet been able to do these tests. Am I right? Or
yeah, we did some very, very preliminary tests on the few bars that survived the trip, because the bars were printed in Padova and sintered in Zeld. That was already quite of a trip for them. We had a target density, a target bending strength, sorry, of 700 megapascal, and I think the survival probability was around 10%. So we're definitely not there yet.
So I think I can mention at least the first name here. So Fabrice is thanking you too for the talk, and is probably part of the Amity project, because
hi Fabrice.
they are thanking for mentioning that. So it's good to have you guys here as well. Then there's a question, what's the voltage needed and how long does it take to scan the ceramics? I think I can answer that. So in that case, these bars weren't too big, and ceramics most of the time, or silicon nitride at least, isn't too dense. So we only needed like roughly 120 kilovolts. In this case, we scanned for quite a long time, since we scanned with high resolution and scanned the whole bar using a so-called helical scan trajectory. And the scan time was roughly 3 hours, 45 minutes, I think. This data is also obviously available in the scientific paper for you to look up. But in general, you could scan these bars way faster in a minute range if you knew what to look for. So in our case, we wanted to have the best possible data for a acceptable amount of time. So we invested quite a bit of time in the scanning, but it could be done faster. But yeah, you don't need much voltage for it. So in that case, 125 kilovolts, I think it was. The next question is, did you try to print in vacuum?
So printing in vacuum would be a bit complicated, because I think it would influence the deposition pattern. Like we still rely on gravity to deposit the material. We could try, I think I would be very interested in trying to mix and degas in vacuum and to fill our syringes in vacuum. That would definitely be of help. We don't have the equipment to do that, but I would definitely give it a try if I could.
Yeah, definitely interesting idea, especially for the ink preparation, like Jota mentioned. But you had a short look at the printer during presentation, and it's also kind of a low budget printer without such sophisticated possibilities like printing in vacuum and so on.
Yeah, Yeah, I think that's also an important point to mention. As you saw in the images of the printer, obviously this is quite a accessible technology still, and this is not like a €500,000 printer, but this is really an accessible way to produce these parts, or at least to do trials with these parts. Then there's some feedback. Some people are thanking you for the nice presentation. Also, thanks for that for that feedback. There's another one from me. What kind of voxel resolution will give meaningful results for AM ceramic printing? So in this specific case, as I said, we use quite a high resolution or high magnification, first of all, that resulting in a high geometrical resolution or spatial resolution. And in these cases, we had a voxel size of 6.5 micrometers per voxel. But this always depends on the application itself. So if you are looking at printing very, very small and fine structures, where very, very small pores would potentially have an impact on the mechanical properties of the part, obviously then you would want to analyze these parts using higher resolution. Whereas when you would probably print or even manufacture in a traditional way bulkier parts where the smallest porosity wouldn't actually have an effect, then you could adapt your resolution. So yeah, resolution always has to be adapted to the application and to the part size. So I think what's meaningful is defined by you as a user or developer of a ceramic application. Would you agree, Georgia and Sarah?
Yes,
definitely.
The next question is, what is the probable reason for the porosity still left in the samples even after sintering at 1700 degrees? So,
I think pores are simply too big.
Yeah, I would guess so as well. Pores are probably too big, and also the cracks that we saw, they just don't close. Can you see differences in porosity if you use different mixing methods for the SN, I'm assuming that's silicon nitride pastes. So can you see differences in the porosity if you use different mixing methods for the silicon nitride pastes?
Interesting question. We haven't checked yet, but we did we tried different ink preparation methods. So this is something that we could have a look at after this presentation. Yeah.
Okay. Then direct ink writing plus VAT equals real 3D printing, not only 2D stacking. What about taking advantage of this to explore new horizons in 4D printing? Any ideas?
I definitely agree. I think it's much more exciting than stacking layers on top of each other. Right now we are exploring the limitations of it. So how free we really are. And with ceramics, I think that would give space to more complex components which could still be produced with less limitations in terms of dimensions and printing area compared to other technology, and probably also cost. It would be really nice to explore also 4D printing in terms of material response, I'm thinking piezoelectric devices, for example, not with silicon nitride probably, but with technology, yes.
Maybe you can just give us a very, very quick quick explanation of what 4D printing means.
Oh, okay. And it's components that will also, normally the fourth dimension is time, so that can also change properties with time or with external stimuli, such as electrical stimuli or mechanical stimuli. They can give a response. So something that not only is complex in the 3 dimensions, but can also give a different feedback after it is being produced, like memory, shape memory, materials, and so on.
Okay, thanks. How long does it take to print a bar? What about the proper tuning of printing parameters like flow rate, pressure, etc.?
Yeah, this very much depends on the ink properties to get the right printing parameters. And as Georgia also said, it also depends on humidity and temperature outside. So it takes some time of tuning. If these parameters change a lot, and then when you find or when you found the right printing parameters, you can start printing a bar, and takes about never really stop, but I think about 30 minutes, something like that.
Maybe even a little less, 20 to 30 minutes, I would say. Yes.
And how to learn how to turn the tune the printing parameters, it just needs some experience. So there's no real rule for it. You just have to test it and try it, and then it gets more easily by time.
Okay, thanks. So is this research also applicable to other ceramic materials? So other than silicon nitride, for example?
Of course. Yes. Direct ink writing is very flexible in the choice of materials. So you need to get that rheological behavior, but you're not really limited in the composition of the powders that you're adding to your suspensions. In this sense, is among the most flexible additive manufacturing technologies. So with Sarah, we did not only experiment with silicon nitride, we also did some attempts with silicon carbide, and it's definitely a technology that can be employed with oxide ceramics as well. There's a lot of work published already on alumina, on zirconia. So there's, yeah, I think the doors are open for all sorts of ceramic materials.
Okay. So looking at the time, I want to encourage all of you who have answered questions, have asked questions who haven't been answered, or if you come up with any other questions, things that that you need to know or want to know, please feel free to get in touch with either Sarah or Georgia directly, as you see here, still shared their email addresses, or with either myself or Gabrielle, so the email addresses that you found in the invitation, and then we will forward these questions to Georgia and Sarah. So please feel free to send over your questions if you have any further ones. And with that, I again thank you very much for attending this webinar. The next webinar session will be on the 24th of August. It will be about CT and R&D of AM parts for stationary turbo machines. And our partners that time will be Siemens Energy. And you can also meet Gabrielle and myself at the virtual Additive Manufacturing Forum this year, and we are also very happy to answer any questions regarding this research that that was done together with Georgia and Sarah. And so that's another opportunity to get in touch regarding this topic with us. So with that, we wish you a wonderful summer. Thanks a lot for attending. Thanks a lot, Georgia and Sarah, for
Thank you
for presenting the work. It was great fun working together with you. And yeah, have a good rest of the day, or beginning of the day if you are in the US, or a good night if you are even in Asia. So thanks a lot. See you the next time on the 24th of August. Bye-bye.
Bye-bye.
Bye-bye.